I'm happy to present our work on emulating space computing networks. It's a joint work with Qing, Yuhan, Zhaofeng, Donghao, Shangguang, Xuanzhe, and Chenren. Low Earth orbit satellites are evolving from large, singular, and expensive nodes focused solely on communication into networked computing systems in space. We term it space computing networks, or SCNs. So SCNs have revolutionized two categories of satellite applications. The first is Earth observation, such as the services of companies like Planet and Palantir. SCNs employ commercial off-the-shelf computing devices for in-orbit image processing, such as compression and filtering, to reduce the volume of data transmitted to Earth. Another application is satellite backbone global connectivity. For example, Starlink, OneWeb, and Iridium are providing global network services. Here, the on-satellite computing enables the satellites as in-orbit computing nodes to perform network functions, including CDN, routing, cellular RAN, and cellular core functions. All these applications rely on satellite computing and networking capabilities. And behind this are two technological trends: COTS chips in space and satellite constellation networking. In the past, satellites adopt specialized chips with low capabilities. Now, satellites are employing commercial off-the-shelf or COTS computing chips, which are a lot more powerful. For example, we had launched a satellite which is equipped with 2 Raspberry Pis and 2 NPUs. Another technological trend is constellation networking. Satellites are no longer limited to low data rate communication, but high bandwidth constellations providing global coverage. However, despite all these advanced technologies in various applications, it is still really hard for researchers to design, build, and evaluate applications for space computing networks. For computing and networking applications, the space is an environment very different from the Earth. As we have mentioned, the COTS chips are more powerful and cheaper. However, they are not specifically designed for satellites. They consume more power and easily get overheated. This leads to performance degradation and even vital issues to the satellite platform. So when designing SCN applications, these points should be carefully considered. By the way, for details on exactly how COTS computing devices behave on satellites, please check our measurement paper on Mobicom 2024. On the other hand, LEO constellations have extreme mobility. They move at a speed at 7.9 kilometers per second. Please imagine what would happen if your cellular base station or your internet router moves at that fast. Also, satellites have a higher failure rate than Earth nodes. So both of these lead to frequent topology changes and unstable network performance. So how do you exactly design, build, or evaluate SCN applications? Basically, there are 3 existing ways. The first is to use real satellites. This provides a real environment for you to carefully consider all the satellite-level characteristics of real satellites. But unfortunately, not everyone has a satellite. There are some open access satellite platforms. For example, we have a satellite which we share with the community for research. However, you still cannot design applications or algorithms at the constellation scale. The second choice is simulators, and probably this is the most popular choice. However, as existing works have pointed out, the simulators lack real software stack or network stack, so users cannot run unmodified applications on it. Also, existing simulators do not model satellite operating environment adequately. For example, COTSIM, one of the most popular satellite simulators, provides inaccurate power modeling according to our real satellite measurement results. Also, they do not provide modeling of the temperature behaviors. So the third choice is emulators. For example, the StarryNet platform published on the NSDI. They rely on container or virtual machine-based architectures to provide realistic software and network stacks. So they are usable for the relatively low cost of the containers or virtual machines. However, these emulators are designed for constellation-scale network emulation, and they lack consideration of the satellite operation environment and the code computation. For example, the power and thermal behaviors are not considered. So we propose RHONE. This is an SCN emulator that achieves satellite-level environment emulation and constellation-level network emulation. RHONE is also scalable and usable. So RHONE works in two phases. In the offline modeling phase, we build models from our real satellite measurement data to describe the satellite operating environment and behaviors. In the online emulation phase, RHONE integrates all the previously built models into a Docker-based architecture. We design aligners to align the code computation and network behaviors with real satellites. Our modeling is based on our measurement study on our real in-orbit satellite. Our measurement data includes 800,000 time-stepped entries spanning over 6 months, and we have released our data on GitHub. So we build models on satellite's power, thermal, orbit, network, and computation behaviors. For the power modeling, we derive satellite's power harvesting patterns of the solar panel and power consuming patterns of each component of the satellite, including flywheels, propulsion, and those computing chips and communication and so on. So our thermal model is based on finite element analysis to model the satellite chip temperature. We built an orbit model based on open source real-time satellite orbit data from celestrak.org and those open source astronomy computing libraries. The network model calculates the satellite network connectivity, topology, link delay, and routing based on the positions of the orbit model's output. As for the computation modeling, actually this is really, really hard. According to our measurement involving 2 chips and YOLO models conducted on a real satellite, we find that the varying temperature, the chip type, and the application can all lead to different performance. The same application behave differently on different devices. For example, YOLO V3 experiences performance degradation under overheat on Raspberry Pis, but this doesn't happen on the Atlas NPUs. Different applications also behave differently on the same chip. For example, YOLO V3 experiences performance degradation under overheat on Raspberry Pis, while YOLO Fastest doesn't. So it is impossible to conduct experiments running each application on each type of chip under various temperature for users to design applications for SCNs. So our modeling approach is based on the observation that the performance of COTS chips, especially the degradation due to overheating, can be mimicked on the ground. This is straightforward because overheating leads to performance degradation, and at the same temperature, both satellite and ground-based COTS chips should experience similar degradation. So we focus on short-duration tasks, for example, object detection, where single executions include only minor temperature changes. And this is typical for satellite in-orbit computing. So our computation modeling goes like this. For each COTS chip, we first remove its fans. Then for a specific application, we repeatedly execute it on that chip until overheat, and cool it, and repeat. In this process, we collect the temperature of each execution and the execution latency results and store in the setperf table. We also profile the emulation physical node. For each application, it executes it under varying resource limits and collects the resource limit value and the execution latency results in the emulator perf table. Now let's move on to RHONE's online emulation phase. RHONE adopts a Docker container-based architecture. We use a container to represent a COTS computing device in the satellite. It means that we use a set of containers to present one single satellite node. So the Docker network emulates the whole satellite constellation network. In the emulation phase, all the previously built models interact with each other to replicate the satellite environment. The orbit model outputs orbit positions of all satellites for the network model to calculate topology. Also, the thermal model uses the orbital positions for temperature derivation. The power model reads current chip temperature T hottest from the thermal model and outputs the chip power value, which is then used by the thermal model to derive the next T hottest. This is the new chip temperature value for the next time step. And the computation model reads the current T hottest temperature to estimate the expected application performance. Now let's talk about how RHONE aligns the emulated constellation with real satellites based on the model outputs. The satellite COTS chip aligner is responsible for computation performance. And when running application 1 on chip A in the emulated constellation, the aligner reads the temperature output, and then it checks the setperf table for expected performance, and checks the emulperf table for appropriate resource share. Then it tunes the CPU or GPU resources allocated to the container node to align the performance. The satellite network aligner is responsible for aligning the container network to the real constellation. So it reads the network model's outputs and dynamically sets the connectivity, delay, and bandwidth of each virtual link in the Docker container network. And we conduct experiments to show that RHONE is scalable and accurate. It scales to over 700 satellites on a single physical node. This is comparable to the state-of-the-art network emulator for satellite networks. And based on the comparison between RHONE's results and our real satellite measurement records, the power and thermal model outputs and the end-to-end performance are accurate. And we now show RHONE's capability of emulating SCNs by 2 use cases. The first case is about Earth observation pipelines. This is a well-explored topic in top conferences recently. Researchers study efficient orbital edge computing and transmission scheduling strategies for low latency and cost-effective Earth observation pipelines. Here we show a case where you can easily explore your pipeline architecture or your scheduling strategies on RHONE. So in this figure, for example, we explored the 4 common strategies: directly transmitting all the images, and in-orbit compression, in-orbit filtering, and in-orbit reasoning. In RHONE's capability to emulate the computation performance, satellite power, and thermal behaviors, and constellation networking dynamics, we can compare the latency, power consumption, and other detailed aspects of the 4 strategies. Another case is the recently hot topic of energy drain attacks. Some researchers have explored DDoS-based satellite energy drain attacks. They take advantage of the predictable topology of a satellite constellation, and then they predict the routing choices based on the topology, and they perform DDoS attacks on a specific victim satellite. They use the routing prediction results to plan the botnet attacks. And consequently, the victim satellites' onboard computation and communication systems operate at the high power level. And this quickly leads to an energy drain. So with our platform RHONE, you can study such attacks and countermeasures very easily, because RHONE provides realistic constellation emulation and with consideration of single satellite power behavior, For example, you can evaluate different attack choices, including starting from the daylight period to or the night period. As satellites harvest power only in the daylight period, so the attack is easier to be successful when conducted in the night period, as the figure shows. Okay, thanks for all your listening, and I'm ready to take any questions.